In video 4.3.4, I want to talk about the null space. The null space is a collection, it's a set. Here's our definition. For a given matrix A, the null space, written null space A, is the set of, oh, I'm missing a letter, gee whiz. The set of vectors x such that ax equals 0. So what does that even really mean? And so we haven't really talked about linear transformations or what matrices do. So let's take a look at maybe a matrix like, consider A equal to, let's see, 2, 1, 3, 1, 5, 2, right? This is a 2 by 3. And if we're going to multiply this by a column vector, if we're going to have, if ax is going to equal the 0 vector, and we know a is 2 by 3, then a 2 by 3 is going to have to be multiplied by an x that's 3 by 1, a column vector. And that's going to give me a result that is the 0 vector that is 2 by 1. So effectively what this is here is a mapping from one space, in this case R3, to another space R2. These matrices are linear mappings. And if you want to think about this as domain and range, the input, if you want to think about this as a function, although it's not technically a function, you can think about it as like, this is like f of x equals y, where we have an input and we have an output. It's not the same thing exactly, but the analogy holds. Here our input is an element of R3, and our output is an element of R2. So it's taking three-dimensional vectors and it's mapping them to two-dimensional vectors. More importantly, this is very similar to, in this instance, we might say y is equal to f of x, but I want to find its zeros. Find the zeros of f of x. Maybe it's a polynomial, maybe it's a function. You got a factor, I don't care what it is. You're just finding its zeros, its roots. And you can think of the null space as being the collection, well, you don't have to think about it as, it's the collection of inputs whose output is equal to 0. And so the null space is the quote-unquote zeros of matrix A. So I just wanted to introduce that concept to you. So up here what we have is a blue vector in R3. I'm just going to call it x, right? And when we apply a to it, we get ax, but that is equal to the 0 vector. And so we're looking for all vectors in R3, in this case, that get mapped down to 0. So let's take a look at an actual example. Maybe I should move this up a little bit. The geometry here is a little bit different. A is 3 by 3, so as far as the geometry is concerned, which isn't really part of the problem, but it's nice to have a good idea of what we're talking about. A is 3 by 3, so x is going to be 3 by 1, and the output is going to be 3 by 1. So we're looking for the set of vectors in 3 space in R3, classic x, y, z, and I want to know what vectors, if any, how many of them are there, x, 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 such that when we apply a and we do a transformation from one space to another space, come on, when we do a transformation from one space to another space, again, we're simply interested in which one of these vectors gets mapped to 0. Not all of them are going to get mapped to 0, but that's what we're looking for. Again, ax. In this case, it's 3 space to 3 space x, y, and z. So this is this particular matrix, the 3 by 3. If you were wondering 3 by 3s, one way to talk about it is a system. Another way to talk about it is a linear transformation that turns vectors into other vectors. So it's the other geometry that we haven't talked about yet. It's actually a lot cooler geometry than systems of equations, but that's the idea. Anyhow, let's go ahead and do an actual example here. We're going to find the null space of A, where A is the 3 by 3 matrix 1, 2, negative 3, 2, 0, 1, 4, 4, negative 5. So how are we going to do that? Well, we want null space A, and by definition, that's the set of vectors x such that AX is equal to 0. So that's where we're going to start. A augmented is equal to the matrix 1, 2, negative 3, 2, 0, 1, 4, 4, negative 5, with a column of zeros on the back end. So I'm just going to use a little bit of row reduction here. We could maybe use determinants and some determinant theory to talk about what the solution might be here, since this is a homogeneous system. The null space question is inherently solving a homogeneous system simply because we want it equal to the 0 vector. But I think the best way to do these problems is always going to be row reduction. So let's see, 1, 2, negative 3, 0. And then I am going to start doing some row operations. We'll do twice row 1 minus row 2 is our new row 2. And that's 2 minus 2 is 0. 4 minus 0 is 4. Negative 6 minus 0 is... Sorry, negative 6 minus 1 is negative 7. Something like that. And then 0. And then we'll do 4 times row 1 minus row 3 is my new row 3. And I will get 4 minus 4 is 0. 8 minus 4 is 4. Let's see. Negative 12 minus negative 5 is negative 7. And 0 minus 0 is 0. And then, of course, the bottom two rows are exactly the same. And so this is 1, 2, negative 3, 0, 0, 4, negative 7, 0, and 0, 0, 0, 0, as I do row 2 minus row 3 is my new row 3. Now, I'm ready to finish this up. I don't actually need REF or RREF form. I can just sort of interpret what's going on here. I know that I have a pivot position in the first and second column that correspond to x1 and x2. And x3 has no pivot. And so that's my free variable. And I will let x3 equal t. Then from the second row, I know 4x2 minus 7x3 is equal to 0. Or x2 is equal to 7/4 t. And then from row 1, I know x1 plus 2x2 minus 3x3 is equal to 0. Or x1 is negative 2 times 7/4 t plus 3 times t. And that turns out to be negative 7/2 t plus 3t, which is negative 1/2 t. And this tells me that x is equal to the vector x1, x2, x3, which is negative 1/2 t, 7/4 t, and t. And I am going to factor out a 1/4 t so that I get whole numbers here. Let's see, that will be negative 2. This will be 7, and that will be 4. And of course, I can just let, since t is any real number, then 1/4 t is also any real number. And maybe I'll just call this s times negative 2, 7, 4. And so that is the set of all possible vectors that when I apply a to it using scalar or matrix multiplication, I will get the 0 vector. And we can double check that. We just have to choose a value of s, so where s is any real number. So, for example, if s is equal to 2, then one possible vector x is equal to -4, 14, 8, and ax will be, can't remember what a is, 1, 2, -3. 1, 2, -3, 2, 0, 1, 4, 4, -5 times the vector -4, 14, 8. Hopefully we can do this arithmetic in our heads. Here we go. This is -4 plus 28 minus 24. Fantastic. -8 plus 0 plus 8. Dynamite. -16 plus 56 minus 40 is 0, 0, 0. Nice check. Good stuff. Proud of you guys. So we might say null space A is the set of vectors x such that x is any multiple of the vector -2, 7, 4. Where s is a real number. Or maybe we might just say it's the set of scalars times -2, 7, 4, such that s is a real number. That might be a little bit more succinct. Either way, same thing. And there you have it. This is the solution.